All right, here we are. We are back for topic 1C, real gases. All right, now as we have mentioned several times before, right, real gases are not the same as ideal gases, right? One of the biggest differences, right, is going to be that real gases are going to have some amount of repulsion and some amount of attraction, right? Depending on how distant they are, right? So if we have a high positive potential energy at very small separations, right? This means that, in this point, when things get too close, they're going to be strongly repelled from each other, right? But from long distances, they're going to be weakly sort of attracted to each other, right? Weakly attracted to each other, right? High positive potential energy indicates that the interaction between them are strongly repulsive. Attractive interactions dominate at intermediate separations, and at large separations far to the right, potential energy is zero, and there's no interaction between the molecules. That would be the perfect situation, right? With zero potential energy, right? This potential energy is going to be like a the voltage between the two, right? And also part gravity, to be honest. All right. So if we look here, easy, right, is we have different isotherms for on the top one of carbon dioxide at several temperatures, right? And so what do we see during these different isotherms? Remember, isotherm means we are keeping the same temperature, right? We're changing the pressure and we're changing the volume, right? What do we see? Well, basically we see that, let's say we're at 20 degrees Celsius, right? See a general curve here, and then we get to some pressure volume relationship here. Well, we have compressed, or we are compressing that gas into a liquid, right? Compressing the gas into the liquid. And then at some point, when you get over here, when it's 100% liquid, that's when the amount of pressure needed to compress the volume even more is increasing, not exponentially, but dramatically, right? Because compressing a liquid or a gas is much, much harder than compressing a liquid or a solid is much harder than compressing a gas. Right? But we also see is that there are some isotherms, like let's say here at 40 degrees Celsius, right, where we never go through that liquid phase. All right, we never go through that liquid phase, right? And so what we see here is that there's going to be some critical temperature, right, which is in this case for carbon dioxide going to be 31.04 degrees Celsius, where we cannot have a liquid above that temperature. Another way of saying is that we can only have a liquid if we are below that temperature, right? So if we have carbon dioxide at 32 degrees Celsius, it can never be a liquid, right? Doesn't matter how much we press on it or how much we squeeze it in, it's not going to become a liquid, right? Only if it's below that temperature can we make an actual liquid, right? It says down here in this is a cutoff just of the 20 degrees Celsius, right? This is talking about the gas condensing in this phase to become a liquid, right? It says it is compressed along the horizontal line, right? And so on and so forth. Go back. So when we're talking about our real gases, one thing we're talking about is the compression factor. Basically, how non-ideal is it, right? So the compression factor Z, the ratio of the molar volume of a real gas to that of the perfect gas at any given pressure and temperature, right? So the ideal gas, Z would equal to 1 because the actual molar volume would be the perfect molar volume, right? And because the molar volume of a perfect gas is equal to RT over P, right? That's just a rearrange of P equals nRT, right? We just rearrange that to V over N equals RT over P, right? we rearrange it to, or in this case, P times V, the molar volume equals RTZ. Right. We basically substituted this in for the moles. Kind of, that's the way we work it. It doesn't exactly work like that, but it's basically the same. Right, so it's like we use this and then we substitute it in this, and we work it all around, right? P times the molar volume equals RTZ, right? Now, for our molar volume, or how do I say this? Oh, we'll talk about that compression factor later. Never mind, we'll talk about that later. All right. Again, all of our gases here, we already talked about the critical temperature, which is what we just saw, 31.0 degrees Celsius for carbon dioxide. Well, there's also going to be critical constants for everything else, every other factor that a gas would undergo, right? Again, this is the critical temperature, T sub C, can only exist as liquid below this temperature, right? If we are below the temperature, we get the normal transition of gas to liquid gas mixture to liquid, right? A normal transition, like B to C here. That's the normal transition. Get some mixture, and then we go to pure liquid. Right, above the temperature, we only get gas. Although gas up here, you notice that it gets steeper and steeper. It's because it starts to act sort of like an extra dense supercritical fluid, right? So it doesn't have the exact same properties of gas, same physical properties of gas, but it's pretty close, right? And if we're at the critical temperature, right here at E, right, if we're at that critical temperature, right, then we would expect to see an indistinguishable mixture of liquid and gas, right? So right here, this is the liquid portion, this is the gas portion, right? We are sitting literally right on the border between liquid and gas, right? Because this one here, right here, right? The blue one is our isotherm, right? So we're gas, we're gas, we're gas, we're gas, we're gas. Now we're liquid and gas. We're a mixture of both, basically. Now, as I said, if we put in the definition of Z into our PV equals nRT. Oh, let's say that didn't make much sense. There we go. I was wondering why this didn't make sense because it was skipping slides. Let's go back a little bit. Keep skipping slides on me. I was like, I know I had extra slides in here. So this is talking about Z. Let's talk about Z real quick, right? At high pressures, Z is going to be greater than 1, right? Again, this means that our actual volume is bigger than the perfect volume, right? Right. So high pressures, these things are being squeezed super close together. And so that's when all of our repulsive forces are going to take over, right? If you go back to this one, right, this is high pressure. This would be when we're increasing the pressure, we're pushing all this stuff together. And so our repulsion would become dominant and everything would start to push apart from each other, right? Right. At intermediate pressures, our Z is going to end up being less than 1, right? Our volume is going to be less than it, quote unquote, should be, right? That's because the attractive forces are pulling the molecules together when they wouldn't in a perfect gas, right? You see a lot of different plots of compression factor when it comes to different gases and different pressures, right? Again, perfect gas has Z equals to 1 at all pressures, right? But all of these approach 1 as a pressure goes towards 0. But they do so with different slopes, not that big deal, right? But the idea is that as the pressure decreases closer and closer to 0, our gases become more and more ideal, right? More and more ideal, right? So we see lots of different, what's the word? Behaviors here, right? There we go. Now, for the result we had before from our compression factor, all right, P times Vm equals RTZ. All right, this is largely going to be true up to large molar volumes and high temperatures, right? And if we get large molar volumes at high temperatures, real gases are basically the same as perfect gases, right? Everything's gonna be moving around so fast that all the arguments we went through with the kinetic molecular theory on topic 1B kind of all get washed. They kind of goes away in a wash, right? And this makes it a good approximation, right? But if we wanted to more accurately calculate the compression factor or any particular type of things, right? We could slice Z into a series of powers, right? Have a variable, in this case, a variable in terms of pressure, right? So as it says, we're creeping up and the most accurate value in a series of increasingly small steps, right? And you'll see this throughout the book several times. It's going to be like, this is like power of 1, power of 2, power of 3, so on and so forth, or sometimes over the power of 1, power of 2, power of 3, right? And we're just creeping up, we're adding together smaller and smaller slices, right? If we wanted to do this, we could this is kind of algebraic way of writing a integral, really, is what it kind of is. All right, in this case, d would be equal to 1 plus b prime plus c prime times b squared plus blah, 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 blah. All right, however many steps we want to go out to. All right. If we put that definition of z into our modified PV equals RTZ, right, then we would get this particular equation, right? This is our virial equation of state. And this is the virial equation of state. This, I thought I have it here, is the virial equation of state. There it is, right? Pressure times molar volume equals RT times 1 plus B over Vm plus C over Vm squared, so on and so forth. All right, all these little constants, B, C, D, whatever you want to call that for that. These are coefficients, and they're all determined experimentally at a certain temperature. Right? All determined experimentally. Basically, what they do is that they find these little coefficients by measuring, the pressure and the molar volume, right? And then they do like a best fit for this particular line. And to do a best fit for the particular line, normally we do a linear thing, y equals mx plus b, right? But you can best fit your line to however many you want, right? You basically say best fit it to this type of form, and then tell me what b and c and everything else would be. Right? Same thing when you do it in this form, it tells you what m and b are. Right? Same exact idea, just slightly different ways of using graphs. Right? And these are all determined experimentally at a certain temperature, right? Because depending on the temperature, we're going to get different interactions. As I said here, right? When we get to high temperatures, everything becomes more ideal. So they're going to expect to change. All right. Now, if we use this, all right, the virial equation of state, pressure exerted by 100 at 100 Kelvin by 0.104 moles of O2 and a volume of 0.225 cubic decimeters. All right, the second virial coefficient of O2 at this temperature is negative 197.5. So one thing to note is that these coefficients are always going to be given to you. Right, they're always going to be given to you, or I guess technically I can have you calculate them. But generally, we're only going to go out to 1 or 2 coefficients, right? Because that gets you very, very close. Let's put it that way. All right. So if our virial equation of state was P equals Vm, right, RT times 1 plus B, let's look, over Vm, right? And then we're gonna cut out C and everything that comes after it because it honestly wasn't given to us. All right, we need to figure out the molar volume. All right, our molar volume. Volume is 0.225 cubic decimeters. Right, our moles are 0.104 moles. That's going to make our molar volume a value of, oh, 1 second, my calculator died. Okay, get out the phone. All right, 0.225 divided by 0.104 gets me 2.16. 2.16. All right. So our P times 2.16 gets me R, which is still 8.314. Temperature in Kelvin, 100. And 1 plus negative 197.5, a value of B, divided by 2.16, right, which is the value of the molar volume. All right. Let's see, 2.16 P. Make this clearer. All right, let's do 8.314 times 100. And this is, right, 831.4 plus negative 197 divided by 2.16. Let me see. All right, if we do that, we get a number of negative 79,019. Now this should give you a little bit of pause. All right, because 831 minus negative 79,000, right? That doesn't make any sense. It's going to give us a negative number. Now give us a negative pressure. That doesn't make any sense, right? Well, the problem is that this number, the units of it are in centimeters cubed per mole, right? Centimeters cubed per mole, right? And our volume, our molar volume is in decimeters cubed, right? So it's not negative 197.5, right? It's going to be divided by 1,000, which is 0.1975, right? Let's do that instead, right? So we do 8.314 times 100 times negative 0.1975, and then divided by 2.16. All right, that gets me an answer of negative 76.019, right? Much more manageable, right? And then when I solve for P, doing this, all right, 831.4 minus 76.019, then divided by 2.16, I get an answer of 349.71. And in this case, we have to think about what do we use for R? We used R 8.314. So this is going to be in pascals. Right. It's going to be in pascals. In book. Yep. 349.71 pascals. We gotta watch for those units. Watch for those units, right? Units are a pain. But luckily, we were able to use our math sense a little bit to make sure that we came out with the correct answer. All right. Now, check. Good. From there, right? we can change to something that's a little bit easier to use, to be honest. Right? So we have the virial equation of state. That was what we just did, very accurate. It's also very cumbersome, right? Because there's lots of different coefficients there. J.D. van der Waals introduced a comfortable in-between equation. So the equation starts from the ideal gas law, but adds in sensible, physically relevant modifications. Right? So some modifications, so 2 of them. Right? The perfect gas law treats gases as points, but we know they have a volume. Right? They have a certain volume that is occupied by number of moles of gas. Right? So if 1 mole of gas is going to occupy, I don't know what volume. It's going to occupy some actual volume, right? And so the true volume is going to be V minus NB, right? Or the volume of the container minus the volume of the particles itself. On the other modification, right, the pressure is decreased when particles veer to interact with each other, right? For different reasons, right? A pressure is when the particles hit the container walls, that's exerting pressure, or when they don't hit the container walls, either by veering off course and taking longer to reach the container wall, or by colliding with each other, right? Well, these interactions are going to depend on the concentration, right? Moles per volume, which is the opposite of molar volume, and the specific attractive forces A of that particle, right? Because the stronger the attractive forces, the more they're going to interact with each other, and the lower the pressure would be compared to a ideal gas. All right, so we can say the pressure decreases by negative or decreasing, right? A times n squared over v squared, right? A times n squared over v squared, right? Because again, why is this squared? Because there's going to be 2 particles interacting with each other, right? So it depends on the concentration of both, basically, right? Concentration of both. That's why it's squared. Right. Now, if we put these modifications into the ideal gas law, we get the van der Waals equation, right? P equals nRT over V minus NB, and then minus A times N over V squared, right? One thing I want to point out, right? I want to point out that this is one thing, and then the other A section is completely separate. All right, so this is not all divisions. Want to make sure that's super clear. All right, A and B are the van der Waals coefficients for attractive and repulsive forces, all right, respectively. All right, the attractive force is going to lessen the pressure. The repulsive force is going to increase the pressure, right? Because this bottom gets smaller and the overall pressure gets bigger, right? And these coefficients are going to be characteristics of the gas independent of the temperature, which is really good, right? That's independent of the temperature. If we went back to the virial equation, right, all of these coefficients were dependent at a temperature, right? So not quite as good. This is going to be independent of temperature, so it's going to be able to be used more widely. Right. Now, some of the features of this is that our critical constants can be derived, right, from it. You can literally look at the book. You can look at all the derivations of it. I'm not going to go through all the derivations because I don't see that big of a point to it, to be honest. All right. But what we can see is that, let's say we talk about a critical temperature, right? Our critical temperature for a gas is going to be 8A over 27B times R, right? Our critical pressure is going to be A over 27B squared, and our critical volume is going to be just 3B, right? So we can, using, we can either measure the critical constants and get the van der Waals coefficients from it, or if we have the van der Waals coefficients, we can use those to find the critical constants. All right. Now, typically, especially if you have a new gas, measuring the critical constants is going to be the easier part, right? Because that's something you do experimentally. Right? A little bit easier to do. And so you use those to find A and B, right, which are independent of temperature. So it works out really well. And if you do an example of this, right, critical constants of ethane, we have a pressure of 48.2 atmospheres, right, a critical volume of 148 cubic centimeters per mole, and a critical temperature of 305.4 Kelvin. You want to know the values of the van der Waals coefficients. Right. So first thing I want to do is that I see atmospheres, right? I see cubic centimeters, and I see Kelvin, right? Pretty much all those are going to be not that great, right? We want all of these, if we use these coefficients, it's going to get us these slightly wrong numbers for A and B, right? Because A and B, since we're relating them in the van der Waals equation to R, have to be in our SI units. All right, so not 48.2 atmospheres, right? Let's see, what was our conversion here again? Right. 101,325 pascals, right? We change that to pascals. All right, that'll give us our new critical pressure, just in pascals. Do that. Let's see. 48.2 times 101,325 gets me 4.88 times 10 to the 6th power. 1, 2, 3, 4, 5, 6. Yes. Our critical volume is in cubic centimeters. Well, to change that to cubic decimeters, we're going to divide by 1,000. It's going to be 0.148 decimeters cubed per mole. Right, make it a little bit easier on ourselves. Now, if you go back and look, there's a very simple place to start with, right? If you look at this, this has two coefficients, right? In this case, we got two variables, right? This would be two variables. Well, the obvious place to start is with the critical volume, because there's only one variable, right? So if our VC is 3B, right, then 0.148 cubic decimeters per mole is equal to 3B. And our B is simply going to be 0.148 divided by 3, which is 0.0493. Right, 0.0493. In this case, it's going to be decimeters cubed per mole. Right, that's the units. Right. That was pretty easy. We got B. Right. Now for A, we have two choices. Right, we can either use the critical pressure, or we can use the critical temperature. Now, technically, what I would recommend, right, for the critical pressure, we changed this number here, right? We changed it into pascals, right? So first of all, it is possible that we messed that up, right? That is possible, right? We did a calculation. There's always going to be room for error there. And then also we rounded that number off just so it wouldn't have tons and tons of digits, right? That's going to introduce some error there, right? So the smarter option here would be to use the critical temperature, right? Because the critical temperature is just given to us as a number, which means we haven't manipulated it in any particular way. Critical temperature is 3A over 27 BR. So we have 3A over 27 BR, right? If our temperature is 305.4 Kelvin, right, we want to know what 3A is. We have 27. All right, our value for B was 0.0493. And then R, always 8.314, right? Makes it easy. And let's do some simplification. Okay, so bottom is 27 times 0.0493. times 8.314, which is 11.067. Right. 3A is going to be equal to 305.4. 3,379, which means that our A is going to be 1,000. Let's do 1.126 with 6 times 10 to the third power. Right? Times 10 to the third power. Right? And if you try to think about our units here, ooh boy, what are units of A? And we're not sure, we can always look it up. Right. Units of A are going to be oh, wait a minute. Units of A in this case are going to be Pascal decimeter to the 6th moles to the -2, right? In this particular version of it. All right, Pascal is decimeters to the 6 moles to the -2. Now, depending where you look up the values, like I just looked it up in the back of the book in the resource section, right? They have A listed in atmospheres per decimeter to the 6 power, moles to the -2 power, right? But it would just be a different, slightly different number, right? Just a slightly different number, right? It would be a smaller number, right? A much smaller number, but slightly different. Right? But that's all there is to it. So again, you can do it. Let me put it this way. If I ask for this on an exam, right, I would probably ask the value to be in atmospheres, honestly. That way I can look it up online and make sure I got the correct answer. That's really the honest truth. All right, something simple like that. All right, here's another example. Suppose that 10 moles of ethane are confined to 4.860 liters, 47 degrees Celsius. Predict the pressure exerted by ethane from the perfect gas law and the van der Waals equation. All right, also calculate the compression factor. All right, for ethane, A is 5.507. Right, and I believe this is going to be given to you in atmospheres. And B is going to be 0.0651. All right, so let's just do the first case, perfect gas law. All right, so we're looking for pressure. The volume we know is 4.860, right? N is 10 moles. R is 8.314. And T, not 27 degrees Celsius, but 300.15 Kelvin. 300.15, right? And if I do that little bit of math, let's see what we get. 10 times 8.314 times 300.15, then divided by 4.86, right, gets me 5,134 times 10 to the third pascals. Okay, again, because we use 8.314 as R, has to be in pascals. Right, now we'll do the same thing with the van der Waals equation. Right, P equals, look back again, right, nRT over V minus NB. nRT over V minus NB. And all subtracted from that, A times N over V squared. Right. We're given the units, well, we can figure that out. Let's see, P is the same, N is still 10 moles, R still 8.314, temperature still 300.15. right? And then on bottom, right, our V is going to be 4.81, sorry, 4.860, right, minus 10 moles times B, which is 0.0651. Over here, A is 5.507. And we'll put brackets here to make it easier. We would have 10 moles divided by 4.860 liters squared. All right, now there's just be lots and lots of simplification here. All right, let's do the right-hand term first. Let's do 10 divided by 4.86. All right, gives me 2.057. All right, square that, I get 4.233 times 5.507. Right, this term is going to be 23.32. 23.32. In this case, pascals. Don't worry about that yet. And then the left-hand term, 10 times 8.314 times 300.15, right, all divided by 4.86 minus 10 times 0.0651, right? If I do that, the left-hand term is 5.9288 times 10 to the third. Right. If I do that number minus 23.32, right, the final pressure is going to be 5.905 times 10 to the third pascals. All right, that's our real pressure, if you would call it that. All right, that's our real pressure. I don't think I have room for it. Nope. And then if we want to do the compression factor last up here, right? Compression factor Z, right? That's the actual molar volume divided by the ideal molar volume in this case, right? Or the actual molar volume. Oh, sorry. Let me go back. Right. Where'd it go? Right. Molar volume with the molar volume. Just want to make sure, super sure. Oh, go back. This compression factor, we're gonna have to come back to it in another video because I need another slide for it, and I'm all out of slides. All right, so we'll stop it for there.